Okay, hi. So I am Yoni Nazarathi from One on Epsilon, and great that you guys joined for the first edition of Math Teachers Code. We will be using JuliaBox and the Julia language, and we'll explore some stuff associated with math education in the context of programming. So no programming knowledge is needed at all. You can either follow along and experiment, or you can try it later. We'll get back in a second to an example that we'll use, but first of all, let's head on to a JuliaBox. So this is JuliaBox, juliabox.com, and it is a free service. There's also a paid version, but it is a free service supplied by a company called Julia Computing. It's a way for us to run the Julia language. I'll speak more about the Julia language as we progress, but that is the language that we chose for this series for Math Teachers Code. So in JuliaBox, first of all, what we want to do is we want to log in, and we'll be running everything through our browser. The code will be running on the servers of Julia Computing. So in JuliaBox, as you get JuliaBox going, you'll see on the top right these login with email, login with GitHub, login with Google, or login with LinkedIn. So choose a method of logging in. I'll do login with email, and if you haven't done this before, you need to actually register. So that's down here below. You need to register. If you have done this, then just key in your email address. In my case, it's mathteacherscode@gmail.com, and then the password and login. If you were logged in through Gmail, then logging in is even simpler. So at this point, what we see is we see the dashboard of JuliaBox, where we can set up some things, packages and Google Drive and other types of things. But basically what we'll want to do is we'll want to launch. So launching asks the servers Julia Computing to set up a dedicated host for us, a dedicated computer for us, where JuliaBox will run. And we wait for a minute or two and get that server going. Okay, so that launch button. In the meanwhile, I'll speak for a sec about the Julia language. So the Julia language just released version 1.0. It's a language that has that's about a decade old since its inception, and many people believe that Julia will become the scientific computing and data science language of the future. It's as easy to use as some languages that you might have heard of, such as Python and MATLAB, but it is fast as C. So it is a high performance, high level language. So a language that's on one hand quite easy to code in, relatively speaking, and on another hand it's just very performant. It can compute things very quickly. I think it's actually also good for math education, and hence this series. Okay, so what you see here is the Jupyter working environment. So this thing, Jupyter. Now Jupyter is not specific to JuliaBox. It is a general framework where we can actually program and run. So this, you might be using Jupyter elsewhere, also using languages such as Python or R or other languages. But in our case, we are in Julia. What we see is a file system. Now, if you just logged in yourself to JuliaBox, something that you might be doing live, but you're probably also doing later, then you'll only see these two directories, logs and tutorials. So for example, if I click on tutorials, I'll see the files inside the tutorial directory. Well, these are other directories. And so if I go to like introductory tutorials, so then, and there's other files inside. So for example, intro to Julia. So these are a bunch of files, these .ipynb files, which you can run later yourself and play with if you'd like, and they are Julia tutorials. So I'm here in the directory structure, tutorials, introductory tutorials, intro to Julia. But I'll move back home. In my case, I have one file called warmup1.ipynb, which is a file that I created about 8 hours ago, but that's not the one we will use. I'm going to create a new file. So for this, I'll go to the New button in the top right, and I can choose to either use Julia version 0.6.2 or version 1.0, and we'll use version 1.0. So when I do this, a new tab opens up in the browser up here, and what this new tab is doing is creating a Jupyter Notebook instance for us on which we can run Julia. So now I'm seeing here in the comments, I'm seeing that people are trying to log into JuliaBox, and Susan Nugget says it keeps asking me to put in a company name. You can just fill in your school name or anything else. So you don't have to put in a company name when you log in to JuliaBox. Oh, and I see that Clara answered that. Thanks, Clara. Okay, so we have here a new tab, a new tab where we have a Jupyter Notebook running, and this is where we're actually going to write our Julia code. So let's just see where we are. Again, we've got JuliaBox here on this tab. That's a JuliaBox tab, and we've got this tab titled Untitled, where we have a Jupyter Notebook running. So this thing is a Jupyter Notebook. So before I do anything else, I'm going to code straight away just so we see that this thing actually runs code. So I'll do for I in 1 till 3, println, hello everyone, welcome to Math Teachers Code. You don't have to do this live. And to run this cell, I hit Shift Enter, and we've got our output. So this was our little program. Okay, we're going to do much more than this, but you see this is our programming environment, and that's the Jupyter Notebook. Now we can rename this Jupyter Notebook. So I do this by clicking on the name, which is currently untitled up here, and I'll rename it Math Teachers Code Session number 1. We'll make these notebooks available after the session, so just follow the comments and you'll see these notebooks. So that Math Teachers Code Session number 1. Okay, and this type of thing where we wrote code inside here, this is called cell, a cell, and that's input cell 1, and the output were these 3 lines of output. Okay. Now if I go back a second to the other tab, we see that we already have the file Math Teachers Code Session number 1.ipynb, and these ipynb are Jupyter Notebook files. Okay, and this file is going to stay on our account. So if I log out now of JuliaBox and then log back in, I can rerun that file. So you can basically do all of your computing. It's certainly good for a starting point in JuliaBox. I find it actually very useful in my classroom. So in my day job, I'm a university lecturer. I'm a senior lecturer at the University of Queensland. I teach courses in data science, statistics, control theory, and probability. And I often code live in front of my students, and having an interface such as this, which only requires the web and nothing else to install, is very useful. So I can do that from anywhere and run my notebooks. So hopefully with this series you'll get some feel how to maybe integrate this in your classroom, also in the K-12 environment. Okay, so we're now back in our Jupyter Notebook, and we've got that one cell. And before I do anything else, I want to make a slightly simpler program. It will be simpler than this one that we maybe don't understand yet, and it will simply be 1 plus 1. So I'll hit 1 plus 1, and to evaluate the cell, Shift Enter. Okay, and we get an answer, and that's 2. So Julia is also a calculator. So each one of those cells, you can treat them in a sense as a program, but it's actually also a bit more than that. So there is, as we are running this Jupyter Notebook, behind the scenes in the Julia computing server, there is something called a kernel running. Now this kernel keeps a state of everything in our program. It knows all the functions that we've created, it knows the packages that we've created, and it knows about variables that we've created. So for example, if we create a variable x and say x equals 1, and then in a different cell I will do x plus 1, then the answer evaluates to 2. So when this in4 was evaluated, x was already set in the kernel as a variable whose current value is 1. Now variables can be local and global, and there's issue of scope of variables, but we won't speak about that just now. Now in a Jupyter notebook you can also format things and make them slightly organized. So the way you do that, so first of all I'm going to create a cell above this cell. So I'll do, I'm going to hit the escape button and then hit the A key, and that meant to create a cell above it. And this cell I won't make it a code cell, but with this pull down menu I'll change it to a Markdown cell. And Markdown is a simple formatting language. Many of you might have heard of HTML. Markdown is kind of a simpler HTML in a sense. So what I can do is I can use these hash signs, for example, and that creates a heading, and I'll say scrap code for warm-up. And when I hit Shift Enter to evaluate this Markdown cell, I get formatted text. I can then edit it again if I'd like, and then say this is the first math teachers code session. Hit it again and it is formatted. We can even do mathematical formulas in Markdown using LaTeX, but I won't do just now. So this kind of says that this is scrap code that it will be using. Now let's go to this cell and convert it to a Markdown, and let's say let's do a heading 1, getting to business, the Hellstone Sequence. Okay, the Hellstone Sequence. So what I want to do today is experiment with an open mathematical problem called the Collatz conjecture, and it has to do with a sequence of numbers called the Hellstone Sequence. Many of you might have heard of this, and for those of you who didn't, let's explore this right now. Now the nice thing about this problem, I actually think it's one of the simplest to explain unsolved math research problems. So it doesn't even require the primes. I mean, many of you have heard about the Goldbach conjecture, but that requires understanding what a prime number, which of course everybody almost does, but still it's a bit more. The Hellstone sequence is something that a third grader can perhaps understand, or maybe somebody even younger. So before we explore it, let's just get to the Hellstone sequence. So this is Epsilon stream. That's an app that we have and one on Epsilon. I'll click Epsilon stream, and I will search for unsolved math research problems. So in Epsilon stream you can basically search for anything in the realm of K to 12 mathematics plus exploratory mathematics, and our content team has curated this content for you. There's some nice YouTube videos associated with it, and there are also some blog posts. In this case I'll click this, and this is a blog post that we wrote more than a year back. So the title of the blog post, "Do Sime Hailstones Fly Forever?" And in this blog post we describe the Hellstone sequence. So let's get to business. So here is one instance of the sequence. I'm now coming from the blog post, and the sequence is 7, 22, 11, 34, 17, 52, 26, etc. Goes on and reaches 1 at some point. Now what's happening here? So the rules of the Hellstone sequence are that if a number is odd, such as 7, then we multiply it by 3 and add 1, so 7 times 3 plus 1, and we get a 22. Whereas if a number is even, then we multiply it by half, or half it, and get half of it. So 11 is odd, multiplied by 3, add 1, we get 34, etc., etc. And that causes some rather well, let's call it non-trivial behavior. This is not an arithmetic or a geometric sequence that acts very nicely. It's a rather wild sequence. Now, as you see here, we eventually get to the number 16, and 16 is even, and half of it is 8, and that's even, and half of that is 4, and that's still even, so half of that is 2, and then half of that is 1. And then from 1 we would continue. 1 times 3 plus 1 would put us back at 4 to 1, and then would be 4 to 1, 4 to 1, 4 to 1, 4 to 1. So there would be something that we can call loosely a limit cycle at 4 to 1. The Collatz conjecture is a conjecture by Collatz that says that from any initial integer, any initial non-negative integer, will end up in this limit sequence 4 to 1. And it's not known if this is true. So there's not a proof for it, nor is there a counterexample, some number where we start and we don't end up in this sequence. So this is a natural thing to explore in this first programming meeting. So let's actually make the Hellstone sequence, and we can even try and find a counterexample for the conjecture. We won't, unfortunately, but we can do other things with it too. We can maybe graph some things and explore some other things. So I found this very useful for introducing open problems to young children, even in primary school, when I visited primary schools to do some expository demonstrations, but it's also interesting for older people as well. Okay, let's get to Collatz. So what do we need? What we need is, if our number x is, for example, 22, then we'll want half of x, right? Or if x is 7, then it's odd, and we'll want x to be 3 times 7 plus 1. So for that, why don't we create a function? Let's create a function, and we'll write it here in shorthand form. We'll say the function is next x. So whatever x is, wherever we are in the sequence, next x will be the next value in the sequence that comes from x. And we'll say next x, and I'll first write it. I'm here defining the function. Next x is a function which says, well, if odd, that's not Julia code, but I'm just writing that, then times 3 plus 1, else half it. Okay, that's what we want to do. If it's odd, times 3 plus 1, otherwise half it. So to do this, we're going to use this kind of operator, which is we'll say, or I'll actually ask, is even here, is even x. Then I'll do x divided by 2 colon 3x plus 1. So the operator that I'm using here, it's called a trinary operator. It's something where here, and where I'm putting a, I'm putting a logical condition before the question mark. If this logical condition evaluates to true, then t is the result. Else, the colon else here is the false, 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 false as a result. So in this case, I'm going to say the next value of x is, if it's even, if x is even, then half x. Otherwise, multiply x by 3 plus 1. And in Julia, you don't even need to have a time sign between a literal 3 and a variable x. Okay. Now before, and if I was now to evaluate this, this would tell the Julia kernel, hey, please create this function next x, which does the following thing. But before I do that, let's actually use this other function that we've assumed we have here, which is even. Is even. So how would we know if a number is even? So for this, well, one way to think of evenness is the remainder of division by 2 is 0. Now, how do we get the remainder of division by 2, or the modulo of division by 2? So if we would do 25, and this operator here, this percent sign, and this by the way, this is common also in C and also in other languages, this type of notation. So 25 modulo 2 gives me the remainder of dividing 25 by 2. Let's try something else. I'll open a cell above. How about 128 or 108? Sure. Modulo 2. The remainder of 108 modulo 2 is 0. So To check if a number is even, what we can do is we can take the remainder by 2 and ask if it's either 0 or 1. So let's create now this function which we call isEven x. This equal sign defines what the function does. And yes, you can here think of a function exactly as a function in the mathematical sense. This is a programming function, but it's a pure function in the mathematical sense that it gets an input and returns an output. Some functions in programming are not exactly mathematical functions because they also change the state of the kernel. But these are pure functions in a sense, the ones we're doing now. So this function isEven will ask if this is 0, will return true. Now this looks a bit weird. Now look at this 0, 0 equals equals here. Now this equals equals is a logical operator. It's not an assignment operator. So it does 34 equals 67? False. But does 34 equal 34? True. So what we're doing here is we're saying the function isEven x is going to check if the remainder of x modulo 2 equals 0, then it must be true, otherwise it must be false. So I'm going to evaluate this cell, and at this point we got output which said isEven. It's a generic function with one method. So we might speak about the phrases functions versus methods. That's more of a Julia specific thing. We'll speak about this later on. But basically this is the isEven function. Let's try it. We now have our function in the system and we can use it freely. Let's see if 7853 is even. No, that's false. How about 654? That's true. How about 0? That's true as well. Okay, so we have our isEven function. So now we're back to our next function. The next function is a function, we're back to our Hellstone sequence. The next function is a function that we want to use to create the next element in the Hellstone sequence. So the way the next function works is it checks if the number is even, then half it, otherwise multiply by 3, add 1. So I've evaluated this cell. Every time I evaluate a cell, I'll put it in the notes, shift plus enter evaluates cell, just so it's clear, right? So shift enter. So that's the way we evaluate a cell. Okay, so we've got our next function. Let's go back to the blog post a second and see. Well, this specific Hellstone sequence started with an initial value 7 and the next value was 22. Let's try it here. Next of 7, 22, that's pretty good. Then after 22 we would do next 22 and we get 11. But something looks a bit weird. What do we have? 11.0, whereas 22 was not 22.0. So what do we have? 11.0. Let's do this. Let's call next 22, let's put that in a variable that we've called out. Okay, out. By the way, variables names in Julia are case sensitive, so this out is not like this out, because this out starts with a lowercase o and this out here with an uppercase o. Okay, and let's use something in Julia which is called type of out, and let's look at the type of out. So Julia is a language with types, and that's one of the reasons that it's significantly faster in performance than some other languages, such as, for example, Python. When we have a variable, the computer remembers what type that variable has. Okay. This specific variable has a type float, which means that it's a rational number in a sense. It's a floating point arithmetic number. So it's not just 11, it's 11.0. Okay, so it's how computers represent numbers that have a decimal point, if you'd like. Okay, that's this out. But let's look at this next 7 here and do this. Let's call this out 2. Okay, and I'll put a cell below that, and I'll do type of out 2. Now you see out2 is of a different type. It's an int64. In both cases, the 64 stands for 64 bits. That's just a number that's represented with 64 bits. But what we see here is that actually sometimes in the sequence we get a float and sometimes we get an out. Now the reason that this happened is because we divided here by 2. Now we divided by 2 knowing that the number is actually divisible by 2. It's even, right? We only divide by 2 if the number is even. I mean, the Collatz sequence, the Hellstone sequence, is designed in such a way that you never leave the realm of integers. You're only dividing by 2 evens. Still, in Julia, even if you take an even number, let's say 100, and divide it by 2, what you get is a floating point number. So division always changes a number into a floating point number, even if there's no remainder. That's a language feature in Julia. In this specific case, it's a bit of a nuisance because it actually means that we're getting these decimal points. Well, we can fix that simply by forcing the result to be an integer. So if I do int 100 divided by 2, then I'm going to get something whose type of is of course an integer. Okay. So this whole discussion was for speaking about the type of 100 divided by 2, which is a float, whereas a type of an int applied to 100 divided by 2, and that is an integer. So if we go back to the function, well, let's fix this now and do int of x divided by 2. Let's read our function again. The function gets x as an input, and it says if x is even, that's that question mark, then return an integer which is half of x. Otherwise, multiply x by 3 and add 1. Multiplying by 3 and adding 1 did not change it from an integer to a float. So I'll reevaluate this cell 13. Notice in Jupyter, by the way, I'm moving here between cells not in a linear manner. I'm just moving up and down. So this was in 24 to the kernel as I reevaluated this cell, and this is out 24. But below we have things that happened earlier. Okay, so now I will clean up just a few of these cells. So I'm going to hit escape and hit X that deletes a cell. You can also do that using the menu. So what I'm using is a bunch of keyboard shortcuts. You can go to the help menu and get keyboard shortcuts. There's a bunch of keyboard shortcuts that you can use. I only know a handful in Jupyter and use them. Jupyter is kind of like the VI editor, if any of you have used VI or Vim editor, in the sense that it has edit mode and command mode. Okay, so I'm going to delete these cells just so we have our core functions here, and I'll even clean things up a bit more. I'll copy this and put it here so that we have everything in one cell, and delete this cell. So now this cell defines the function is even and defines the function next, and we feel perhaps a bit happy now because we can at least manually play around with this Hellstone sequence. We can try and reproduce this sequence using our next function. Let's try to do that at least to a level. Let's do x equals 7 and then next x. We get a 22. Now every cell when we evaluate things in a cell, the last expression that we had in the cell is a thing that appears as output. So if I would now do again, let's do x equals next x, and now do x equals next x again. So we see x started at 7. This line here changed it from 7 to 22, and this line here changed it from 22 to 11, but what we see is the last thing. I think what we wanted to do is maybe something like x equals next x, and then how about if we would do println x, and now this is of course an intermediate thing, println x and println x. I'm going to hit escape and hit the L button so we get line numbers. So line numbers are not part of the program, but they just allow us to, if we're sitting next to somebody, or in this case me live streaming to you, line numbers just allow me to refer to different lines. So in line number 1 we set the variable x to be 7, in line number 2 we printed that. Let me run this. In line number 3 we set the variable x to be next applied to the variable x, right? It's a recursive definition of the sequence. In line number 4 we printed that again, and in line number 5 we did that, and in line number 6 we printed again, and we see our 7, 22, 11, and we're getting 7, 22, 11. We're heading up this sequence. Okay. Of course I can continue this, and I can copy paste, and I can do more and more and more. And get 7, 22, 11, 34, but why should the program be so long if we could automate it? So for this, let's introduce a loop. Even if you've never programmed before, it's already evident to you that one of the useful things of computers is that you can make them do things again and again and save manual labor. So in this case, let's start with not the right loop to use here, but the easiest loop in a sense, and that's the for loop. So what we can do is we can do a for I in 1 till, let's say, 10, println I, and the way this loop runs is lines 1 to 3 iterate 10 times, where the variable I gets the value 1, 2, 3, 4 up to 10 in there, and in the process we do anything we want. So we can have as many lines of code as we'd like here. We can have, for example, x equals 67 and y equals x squared, and we can run this, and that's fine, it still ran. It's just that lines 2 and 3, even though they occurred during the loop and they occurred 10 times, nothing was interesting with them. Okay, and the value of I changes. Now I started this session today with println some text. I think I said something very basic. It was like this string. A string is a combination of characters within quotation marks, which is actually human text and not machine text. Okay, so this repeats line number 2 10 times. Now notice that in this version of the loop we actually didn't use the value of I, so you can actually make that a bit more explicit by replacing I by an underbar. Okay, so for you don't care what, repeat this please 10 times. Okay, now let's use this type of loop and replace the inner line of the loop with x equals next x and print line of x. Okay, and let's start x, for example, at 7. Okay, so before we run this, let's see what we expect to happen. So as we start in line number 1, the variable x would be set to 7. Then lines 2 to 5 will make lines 3 and 4 repeat 10 times, and this is not the right loop to use because we don't know a priori how many elements we need. I mean, are there 10 elements here? Are there 20? Maybe there's an infinite number. That's a conjecture. We don't know. Well, the conjecture is that there isn't. Okay, and then line number 3 sets x to be the next value of x, and then we print x. Or maybe it's better to actually print x first and then set x to be the next value, so this way the 7 gets printed too as well. Okay, let's run this, and we've got 7, 22, 11, 34, 17, and this is starting to look like our Hellstone sequence. The only problem is that we ran only up to 20. So if I was to change this 10 to be an 11, we'll run 11 iterations and we'll get the next value, and we see, oh, the next value is still not 1. We can run this to do 12 iterations, and the next value is 5. That's still not 1, and we need to experiment with this. So this is maybe not the perfect loop to do, but it's already a good start. Another small change we can do, instead of doing println, let's println x, and we won't be satisfied with this, but let's see what this does. This puts the numbers one after another. The problem is that we can't separate, we don't know that this is a 7 here and following it is a 22. So how about we print x comma a space after the x, and this is maybe more satisfying. Okay, so we're starting to get to where we want to, but our issue is this loop which runs a fixed number of times. So for this, let's introduce a different type of loop. So I'll call this, I'll put note above this, and let's call this in a markdown cell loop attempt, maybe 1, 2 O's, loop attempt number 1, loop attempt 1. Okay, and here let's create a better loop for this case, and we'll call this, we'll just label it a more suitable loop. So the other type of loop statement that we have in Julia and in many other programming languages. So what we see here has not been, I mean, the syntax is very Julia specific, but C, Python, R, JavaScript, MATLAB, Swift, Go, many of these languages would have similar constructs, certainly at the basic level. So I'm going to paste this code again and replace this for by a while. So I'll do while x does not equal 1. So this is the not equal logical operator. It is the friend of this equals logical operator. We've used an equals logical operator up here, and this is a not equals logical operator. And the way this loop works, it doesn't work for a fixed number of iterations, 1 to 10 or 1 to 20. It rather repeats lines 3 and 4 a number of times, which depends on this condition. So the program would start at x equals 7. Then in line number 2 it would check, does x not equal 1? Yeah, 7 does not equal 1. So then it will execute this block of code that I'm highlighting now. The end statement will make it pop back up to this while, and we have our new x, is it not 1, etc., etc. So let's run this, and we're pretty satisfied. We didn't print that last one. Why? Because finally when x was 1, we never printed it. So what we can do for this is we can put another print statement out here, which would print x. And this block of code is a full block of code that creates the callout sequence for any desired initial value. Now some other things to note. Any desired initial value that you set in line number 1 to be 7. And notice that I used indentation, and this is common programming practice everywhere. So inside, it's not necessary in Julia, but it's certainly the right way to do it. So inside the while loop I indented so that a programmer comes and reads this and sees, oh okay, lines 3 and 4 are inside the while loop. It's kind of immediately obvious when you look at it from afar. So often you'll see sloppy or beginner programmers programming like this, but this is much less verbose than this. So things get indented. Let's start with a very popular, let's start first of all with maybe 32. So if you work on the callouts conjecture and the Hellstone sequence with children in class, an interesting thing to note is you can ask, hey, on what number will you only get lower and lower and lower in the Hellstone sequence? And then kids kind of think, the number needs to be even because then you have it, but it needs to continue to be even. And quite quickly they realize that, or somebody in the class would get to that realization that if you start with powers of 2, then you're shooting down very quickly, right? You could start with a higher power of 2, like 4096, which is 2 to the 12th power, and also shoot down. A common starting number is 27, a popular one, because you actually get very, very high, and this kind of shows the craziness of the sequence, right? I mean, 27, we had a very long sequence until we hit the number 1. I mean, it's very different, from example, from 26, which hits one very quickly. And you can now experiment with this for any initial starting value that you'd like, in a sense. Now let's put all of this in one function, and let's call this function our print Hellstone function. Okay. So what I'm going to do is I'm going to define a function in a slightly different notation than this notation. This was kind of shorthand notation for defining a function. These were one-line functions, where what I'm highlighting now is the inside, or the implementation of the function is even, and this is the inside or the implementation of the function next. But more generally, what you would do is you would write something like this. You'd say function, and you'd call it, say, print hail with an initial value of x. So I'm going to delete this line, and I'm going to also hit command right brackets. I'll put that in the comments. Control or command, I'm on a Mac, this or this for indentation. So square brackets for indenting. That's just a way of editing. That's in many editors, by the way. So now lines 2 to 6 are the implementation of another function that we've created, and this function is going to be called print hail. I'm going to run this, and it says print hail generic function with one method. And basically we took the code that we had before and we put it inside a function, then we could use it again and again. So if I will do print hail, for example, of 7, we get the sequence that we had in the blog post. Print hail of 32, etc., etc., etc. Good. So that already gives us a computational mechanism for at least manually checking if the Collat's conjecture is true. Well, we can't check if it's true, but at least looking for a false statement. So if, say, we believe for some reason that this big initial value is going to never terminate, we expect the program to never terminate, but no, it gives us something that terminates. But let's do something a bit more. Let's actually take the values of the Hellstone sequence, put them in an array, in a collection of numbers in an array, and then make a plot of them. Let's do that. So for this, we don't want to print to the screen. We rather want to collect values in an array. So let me show you what I mean by an array. This is my array. This is some array. Here's an array of numbers. Okay, so an array is a list of numbers. Okay, it's a list of numbers, or a list of elements more generally. It's a list of objects. This is an array of int64s, and it has a value 24562. Now we might want to here make a function that instead of printing the values of the elements, puts them in the array, and let's just create an alternative function like that and call this hail array if we'd like. And this is how we would do it. We'll start with an array. We'll say rout is going to be starting in line number 2. So I'm going now with something that's slightly more advanced. Okay, rout is going to start just with the element x. So let's say x, we gave 7 as an input to this function. It will be the first thing in the array. Now here, what we don't want to print x, so I will delete this line. Now instead of deleting it first, let me just comment it so you see how you comment. So if you do a pound in Julia, that makes the line a comment. That actually commenting is of course for adding comments in the code. Like here I can say x is the next value, for example. That's a comment, but commenting is also useful for turning lines off temporarily before we delete them, or something like that. Okay, so instead of printing x, what I'm going to do is I'm going to use a function push, and this function push will push to the push exclamation mark, that's the name of the function, and it would push into array out the value of x. Okay, I'll show you how to get information on this push in a second. And at the end, what we're going to do is we're going to return the R out. So the return statement tells the function, please return this as the value that the function computes. In this function, it's an array. Now, actually, we could have not had it. The last element of a Julia function, or the last line of code, is a return value, but this is a bit more explicit for us. Okay. And for reasons that you might see, if you think about it, I think it's better that we actually have the x equals next before the push, because then the last element, the 1, would be pushed in as well. So let me delete this line and delete this line. Before we run this, let's actually think what this is going to do. So Hail array is a function. It gets in an x value, say 7. We start with array out is going to be the element 7. We're asking, does our x, does our 7 not equal 1? Yes, it doesn't equal 1. So 7 equals the next element to 7. Next is already defined up here. Right? Next is this. This is next. That's the next element of the Hellstone sequence. Fine. Then we're going to push x into array out, and we're going to continue then and do this until x does equal 1. When x equals 1, we're going to stop, and then line 7 will return array out. I'm going to evaluate this cell, and let's try Hail array on 7. And what we got is, well, we got a printout, but that printout was a printout of the array. Okay, so this is actually something we can work with. So let's call that from example out from 7. And if I put a semicolon at the end of the line, that suppresses the output. Okay, so this out from 7 equals Hail array 7. I now have an array in the system which is called out from 7, which is this array. It's very different than just printing it, because now we can do something with this array. Okay, that's out from 7. Alternatively, I could have also had, if I would like, out from 27. That would be Hail array on 27. Okay, so that's out from 7, and that's out from 27, and that's a different array. This is a 112 element array. There are 112 elements, and we don't see them all. They're dots here in this array. Okay, that's out from 27, etc., etc. So what can we do with this? Well, first of all, we can plot things. So for this, let me delete this cell, and I'm going to call using PyPlot. So the using command tells Julia, please use things from a package. In this case, a package is called PyPlot. It's actually the Python plotting package, which is the package, the basic package for plotting with Julia at the moment. Okay, so using PyPlot. And now let's first of all do n to be the length of out from 27. Just so we get a variable n, which will ask how many elements are in out from 27. So when we started with 27, there were 112 elements in the Hellstone sequence. And now what we can do is we can plot, where in the x coordinates we'll use a range of values from 1 to n, so that's 1 to 112 in this case. And in the y coordinates we'll use out from 27. And this is a basic plot. And I think that if you do such a thing live in front of your students, they can often be quite impressed, because as I do things live, as you see even now, nothing's perfect. Sometimes I don't write the exact thing, or there's a mistake or something like that, but students actually find that engaging, and the end result is nice. In this case, what you see is this is the Collatz, the Hellstone sequence, starting here at the first element around 27, and going up to a value which is almost 10,000 until it flies back down, back to 0. So this is something you can do with that. Now, if you just want to automate this a bit more, then let's just do here out equals Hail array of start equals, say, 27, and how does Hail array of 27 of start, and call this out, and call this out, and I'll delete this line, and it's all just a bit cleaner. Okay. I'm almost about to stop. Let me just fill in just a few last details. So we use the function called push exclamation mark. Now in Julia in general, you can get help for functions by using question mark and put the name of the function. So question mark on push exclamation mark. Exclamation mark is actually part of the push function, and that and here you have some examples of how to use it. So you can do a question mark on many other things, okay, and get help like that. Now in general, if you head up to julialang.org, so that's the website of the Julia programming language, julialang.org, what you can do is hit documentation, and you are going to get the full Julia docs. Okay, you can change between version 1.0, 1.02 in this case, or earlier versions, but you probably just want to work with the latest version. And you kind of get, so if you go, for example, for control flow, you're going to get examples on how to do loops and conditional statements and functions and the rest, and there's a full Julia documentation. Now this is a rather technical thing. I mean, it's very well written, the Julia documentation, but it's rather technical, so it's probably not the best way to go. So then some other resources. So one way to go is, of course, tutorials such as this one, which kind of go all over the place but try to give you examples of specific things. Another thing is here in your JuliaBox, go to the tutorial section. I've shown you this before, but maybe now it makes just a bit more sense, and go to introductory tutorials, intro to Julia, and use a few of these tutorials. That's another thing. There are also some great YouTube resources. There's a tutorial by people at Julia Computing and others that kind of give in-depth tutorials. You can also look at a draft book. So if you Google statistics with Julia, so this statistics with Julia, so this book, which is still not out, but the draft is out on the web. It's going to be published via Springer, and then the draft won't be on the web anymore. That's a book that a partner of mine, Hayden Clock, and myself were writing, and that's Exploring Julia Statistical Primer. You'll actually see an example of the Hellstone sequence there. So this is a book where we're actually doing statistics, but what you see is a variety of code snippets and that are not exactly designed for the beginner, but they aim to teach you statistics and Julia together, but you do need to know a bit of Julia for that. And perhaps the best thing to do is to play around. Let us know how you go. Next week we'll continue with elementary things, and this is the first week out of a series of 6. And I think I'll pretty much end here. Let me just remind you, if you like this, please share with others. Please visit us in One on Epsilon and see what we're about. We would love if you would try our Epsilon Stream app, share it, like us on Facebook, etc., etc. And I think that's it for me now. So that would be it. Yoni Nazarathi, see you next week. Bye-bye.